Here we have a picture. I believe you can see this dot here. Now question is this dot inside the bounded region or outside of it? Let's understand this question closely. And this question will reveal beautiful insight in mathematics. So let's first remove it and see something simple. Let's say you have this circle-like object here and it's point A and it's point B. Now tell me, is this point A outside or inside this bounded region? Obviously, it's outside of it. And what about this little point B? It's obviously inside. Now, this problem about circles is pretty simple, but the problem we previously see that the wheelie curly lines, loops, that were pretty complex. So, how do we find a general solution to this kind of problem? Here comes the Jordan-Brouwer Curve Theorem. This theorem helps us distinguish inside of a bounded region and outside of a bounded region. So let's see what can we do. What if we cross a ray from this? And now, as you can see, this ray crosses this region and here you have two intersections. We're going to name it 1 and 2. You can see that just a little bit over this one point here, it's a little bit over and pretty close to it. This dot is inside the circle and here is 2 and 2 point little over we have this dot A and A is outside, B is inside. You haven't seen much thing, right? Now let's see something that unveils more things. Now you have this diagram and we have to consider a single loop, no overlapping like this. This loop is forbidden. We only will have a single linear loop, single and simple loop. Now we have point A, point B, point C, point D, and point E. Now if we project a ray from here and we have some more intersected points, let's name it 1, 2, 3, 4, 5. Now if you see that this point 1, a little bit slightly over this point 1, we have a dot which is inside. Here we have 2, little over 2 we have another point which is outside. Little over 3 here we have a point which is inside, and little over 4 we have a point which is outside, and so on. Now did you see the pattern? Hopefully you've seen it. If you haven't, no problem. First point and little over that point or intersection number, we have a point which is inside, 2 it's outside, 3 is again inside, 4 it's outside, 5 it's again inside. Here we have a pattern. If your intersection number is odd, then over that intersection, slightly over, we have a point which is inside the bounded region. If it's even, then that point over the second intersection will be outside the region. And so is true for all the other points. This is just a basic formulation of Jordan-Brouwer Curve Theorem. Now let's see, get back to our previous example, if we can find it out with this. It's a pretty powerful example and theorem. What we had is something like, notice here we have no overlapping and twirls, curls. We just have a single loop. As you can see, a rope connected to one end to another end. Now we have a point A and another point B. If you project a ray, here it's number 1, here it's 2. And as you can see, 1. According to our formulation, this point A must be inside this boundary region. Let's see if it's true. If A goes this way, it's stuck. That means it's inside. If we go this side, it's again stuck. So it's inside. But what about the point B? Little point B. If this point B goes this, oh, it's outside. That means our formulation is correct. It also works for all the other complex shapes like this one or this one. Regardless of the angle or position, you can draw any ray as long as the loop is non-overlapping and simple. And now let's bring it to the higher dimensions. Spheres can be projected on this 2D board, so let's think about it. If you have a point here and a point here, you draw a line. Draw a line here. It's pretty hard. So here is the first intersection, here is the second. Point 1, point A, point B. And here, if you name this 1 and 2, this one is odd, so little over that we have the point A, and A point is clearly inside the sphere. And if here we have the second point, which is even, and over that we have the B point, which is clearly outside the sphere. Why didn't I choose this? Because it's just an illusion as we are drawing in the 2D board. If you try it using real 3D objects, it would be much clearer. Now let's understand with this marker. Here, if you slice the marker in two, we get two edges or 2 points. The point 1, over that point we have, over that intersection, the first one, we have a point, and that point is clearly inside the marker. And here we have the second, and the second point is clearly outside, or the second intersections over a point which is clearly outside this marker. And that's why that theorem is so much powerful. It's regardless of the dimension, regardless of the axis, or regardless of the shape, the space. You can see it in hyperbolic space or spheric space. All the things will work as long as you are assuming a single loop which is non-overlapping. And this thing also works in fourth dimension, fifth dimension, and all the others. Why does this work? Now let's find it out. It works in every kind of plane because the definition of our inside and outside is the same everywhere. That's why the theorem doesn't change. And now let's understand why the theorem works in the first place. Now let's assume this. Here you have a wiggly shape, and as you draw this kind of shape, you're basically dividing the space in three parts. One part is here, one is here, one is here. And if you draw a ray, this is the first point, this is the second point. And the first point must be inside this. Haven't we bounded it? This here and this here. This point must be bounded by this. And if you have this B point is over the second intersection, which is even, so this point is clearly outside. And that's why this theorem works in the first place. Hope you have enjoyed it.